Hello students, good morning and welcome to the Mechanical Engineering Department of Galgotias University. I am your teacher Dr. PKS Nain for this course Mechanics of Material with code BTME2008. As the topic suggests, it is the first course in this series called Introduction to Stresses. If you look carefully, this is the second course in this succession. In the last semester, you have studied engineering mechanics course, which was the prerequisite to this course. And this course, Mechanics of Material, will lay foundation for more advanced courses which will be taught to you in third year and final year. In third year, you will be introduced to the advanced course which is based on this course with name machine design. And then in the sixth semester, you will be taught another course based on the same course which is design of transmission system. In final year, you will be studying CAD as well as the finite element analysis as an elective for which this course is also a prerequisite. This course is a very important course for all the students of mechanical engineering, chemical engineering, automobile engineering, as well as civil engineering. So let us begin our journey of digital learning in the course of Mechanics of Material, and I will be taking you through this journey. Let us hope it will remain pleasant for both of us and it will be enjoyable learning path for all of us. It remains very important that what should be known to us prior to studying any course. That is known as prerequisite of that course. In this course, what I require you to revise and understand that I need certain basic knowledge of physics laws like Newton's first law, Newton's second law, Newton's third law, the equation of motions, law of gravitation like that, and then I need the knowledge of mathematics because we will be using some differential calculus as well as the integral calculus in this. And then we will be solving some differential equations when we will be using the theory of columns towards the last part of this course. And as I said in the beginning of this lecture, this is the second course in its series. The first course is engineering mechanics, which you have studied in your third semester, which was your last semester. And so let us go to our journey ahead. I'm sure that most of you know these courses very well and you have already cleared those courses. So you are well prepared to start the journey. The objectives of today's lecture are to identify various types of loads or forces which can act on the body and define the stress and shear stress and try to visualize it. So let me introduce to the subject, which is strength of materials. It is also known as mechanics of materials. So generally people call it SOM or MOM. What this subject is all about. So the first point is that it deals with the strength or the load carrying capacity of various members such as beams and columns. So most of these structures, whether it is mechanical structure or it is a civil structure or a chemical machine, chemical equipment, most of them are basically we are worried about the strength of our machines and the performance of the machine. So how to know whether this machine is going to sustain this load or not? So that is the way where you will like to know the strength or the load carrying capacity of various parts or various members, which are called in structures as beams and columns. What are beams? Beams are basically the structure members which carry lateral load perpendicular to them. So along the longitudinal axis you will have a beam, and then it will carry the lateral loads. While a column, on the other hand, is a structural member which you might have seen in many buildings, is generally vertical, and it carries the compressive load. It carries the compressive load, and mostly it is vertical in any structure. So basically, from this foundation we are going to expand this subject that we are worried about. We want to ascertain the strength of the material or strength of the members which are going to sustain the load for the exact performance or the correct performance or the proper performance of the machine or any structure. Well, the basic purpose of any member is to support a load. A load can be applied on a member like beam or column in various forms. The first of it is the point load. What is a point load? So let us define the load first. A force acting on a body is termed as the load. So this is the primary definition. Load is a force. So naturally, what would be the units of load? It would be same as that of force, that is in Newton, or the weight in newtons. The concentrated load, which is also known as point load, is the most popular load used in strength of materials. You see what I mean by concentrated word. If you look at this figure where I have shown you two circles, one is the yellow circle, dark yellow circle, and the blue circle. The blue circle is showing the area of the member, cross-sectional area of the member, and then yellow force is pulling it in order to increase its length. So if you look at the yellow area as compared to the total blue area, the area over which this force is applied is shown in a yellow circle, and that is pretty small as compared to the whole blue cross-sectional area of the beam, and hence this will be termed as a point load or concentrated load. So what is a concentrated load? If the force is acting on a very small area of body, then only you will term it as a point load or concentrated load. Now the point load can be of two natures. One is the tensile load, which is generally denoted by a positive symbol, and the other is the compressive load, which is generally taken as a sign convention, negative load. So a tensile load, if you look at this, if yellow forces, the two equal and opposite forces are pulling a blue bar, so they are trying to increase or stretch its length. When the length is increasing, this kind of load is known as tensile load, and it will cause the increase or tend to increase the length of the member. While on the other hand, if you look at the second figure at the bottom, which is titled with compressive load, you will find that two equal and opposite forces are acting on two extremes of the member, which are trying to reduce the length of the bar, and hence they are trying to compress it, and hence it is called compressive load. So if you look at the tensile load, the length is going to increase or tending to increase, hence it is a positive increment in length, and hence it is considered a positive load. While in compression, the length is going to decrease, and the decrease is the negative increment, and hence it is known as the negative load as per our sign convention. The other kind of load, which is not the concentrated load or point load, is known as distributed load. In a distributed load, a load is applied over a length. Okay, when the load is distributed over length, and then it is known as a distributed load. Means the force vectors are acting over length or the span of the length, span of the beam. Then it is known as distributed load. Once again, the distributed load can be of two types. One is the uniformly distributed load, and second one is uniformly varying load. So if you look at the figure on the left, you will find it is a beam where it is a horizontal member is placed in the so this is the longitudinal or the horizontal direction is the beam, and the vertical or perpendicular loads are applied over a length of 2b vectors. So 2b length. So but the magnitude of all these force vectors are constant, and that is W naught, and hence it is a uniformly distributed load. Uniform because the magnitude of the load is uniform and constant at W naught. Distributed because it is a distributed over a length of span of 2b meters of the beam. So it is a uniformly distributed load. Uniform refers to the magnitude, distribution relates to the length over which it is acting, and load, it is acting perpendicular to the longitudinal axis. Then second one, the figure on right hand side, you see the vectors on on one extreme is having 0 magnitude, on on the right hand side they are having a maximum magnitude. So this kind of loading is a triangular load. Vectors are the magnitude of vectors. If it is denoted by length of the vector or the arrow, then you see the length of arrow or the magnitude at one end is 0, at other end the magnitude of load is maximum. So in between it is varying linearly. So you will call it a uniformly varying load. Why it is uniform? Because the rate of variation is constant. So hence it is a uniformly varying load, and it is a distributed load of uniformly varying type, varying at a constant rate. That's why it is known as uniformly varying distributed load. So this is the two type of distributed loads which we will be generally coming across in this course. Equilibrium conditions. Basically, when we talk of a coplanar non-concurrent force system, like the one figure which I have shown at the bottom, there is a horizontal beam with its length as the longitudinal axis, and perpendicular to it a W naught weight vectors are acting over a length of 2b in the transverse direction. So you see all these blue vectors of W naught magnitude, they are coplanar but not concurrent. They are not passing through a single point. And hence, generally beams constitute a coplanar non-concurrent force system. So for such force system, we already know the equilibrium condition from engineering mechanics is that summation F should be equal to 0 and summation M equal to 0. Summation F equal to 0 represent basically two conditions, two equations, which is summation of horizontal forces should be equal to 0 and summation of vertical forces should be equal to 0 for two-dimensional force system. The second condition is, which is Basically, third equation of equilibrium is summation of moment about any point should be equal to 0. So these three conditions together represent the equilibrium conditions for coplanar non-concurrent force systems like the one which is shown in the figure at the bottom. If the force is acting along a longitudinal axis, then it is known as direct or axial load. So what is longitudinal axis of a beam? That is the length axis of the beam. Axis parallel to the length is and passing through the centroid is the longitudinal axis. So if you see, the yellow vectors are pointing in the axial direction or the longitudinal axial direction, and they are known as the direct loads. The direct forces can be of two types as we are showing. One is the tensile, which is increasing to tending to increase the length of the beam or the bar, and second is the compressive force or the compressive load, which tend to reduce the length of the bar. Normally the beams are subjected to loads normal to their longitudinal axis, hence they are known as transverse load. So you see W0 vectors which are shown in the bottom figure, blue W0 vectors over the length of 2b, they are representing transverse loads on the beam. And these are the two types of loads. One is the direct or axial load, which can be tensile or compressive, and then we have the transverse load on the beam. Consider a cylindrical body which is subjected to equal and opposite force shown by the green arrows. They are acting at the center axial axis, and it is called uniaxial loading along the longitudinal axis. They are trying to stretch the body, but internal forces are trying to resist the deformation. If you cut this body by an imaginary plane, you will see the yellow interatomic forces, which named as cohesive forces, are trying to resist the green arrow in the opposite direction. If you see the other part of the section, the same is the story there. So, for equilibrium, the green left arrow, which is shown on the screen, should have the magnitude equal to the internal yellow forces. So the effect of these two forces should be equal and their magnitude should be equal for the equilibrium. However, we see there are few arrows here, but it can be distributed into multiple arrows because the number of interatomic chains which are providing the resistance are numerous in such a small cross-sectional area. Hence, we can always say that it is better not to consider just the load, but to consider the distribution of internal forces within a body which are trying to resist the deformation. So mathematically, the stress is a quantity which is defined as force per unit area, and the unit of which are Newton per meter square in SI system of units. It can be expressed as Pascal in SI system of units also. So you remember the internal forces, yellow forces, are normal to the surface, and hence this is known as the normal stress. And the magnitude of it is equal to F upon A, denoted by a word sigma. Sigma equal to F upon A. The general assumptions which are made during the stress analysis is then that when a body is subjected to the external forces, a body is considered to be perfectly elastic. What does it mean? Whenever you remove the action which is causing the deformation or the external force, the body tries to resist and return back to the original undeformed position on the removal of load. So this is known as elasticity of the material when it is trying to recover its original shape on the removal of the external force, and hence the body is considered to be perfectly elastic. Second assumption is the material is isotropic. Isotropic means the properties are independent of direction. Whether you are moving in X direction or Y direction, the properties are same. They are independent of the direction. And lastly, the material is considered to be homogeneous. If you take the sample of material at different locations in the body, the chemical composition and the mechanical properties all come out to be same at each and every point. So the chemical composition is same at every point. The material is considered to be homogeneous throughout the volume. So these are the three general assumptions. The body has to have perfectly elastic. The material is isotropic, that is properties are independent of the direction, and the material is homogeneous in composition throughout the volume. So as we have seen in the video, that stress generation basically comes from by the virtue of cohesion force between the particles. So all the external forces on the body are transmitted to support through the material of the body. This phenomena tends to deform the body and cause it to develop equal and opposite internal force, as it is shown in the figure. These internal forces are generated by virtue of cohesion forces between the particle, and they tend to resist the deformation, as it is shown in the bottommost image. The magnitude of internal resisting force should be equal to the applied force but opposite in direction. For equilibrium, if you consider this figure, summation of horizontal forces should be equal to 0. Means the force P to the left should be equal to the resistance R to the right. And from this you can say R should be equal to P. So that is all about the important point about the stresses. So the resisting force per unit area of the surface is known as stress intensity, or simply stress. It is denoted by sigma, and sigma is defined mathematically as P by A. If you consider the elemental force delta P and the elemental area A delta A, which is resisting the deformation, then in limit delta A tending to 0, delta P by delta A is considered to be the value of the stress. The tensile stress, which is characterized by increase in the length of the object, they are considered positive, while as the compressive stress, which are related to the reduction in the length of the body, are considered as negative. Their signs depends upon nature of force applied on the body, whether it is a compressive force or it is a tensile force. So its stress has unit of Newton per meter square, and 1 Newton per meter square is equal to 1 Pascal. As you see, 1 Newton over an area of 1 meter square is a very small value for practical applications. We generally consider 1 megapascal or 1 into 10 to power 6 Newton per meter square as a normal unit for the stress, and sometimes we also use 1 gigapascals, 1 GPa, which is equal to 1 into 10 to power 9 Newton per meter square. Shear stress. So far we have considered direct stress, which are acting along the longitudinal axis. But now we will consider the two equal and opposite parallel forces which are not acting in the same line. consider this force P, which is pushing the body towards the left, and the other opposite, equal and opposite force P, which is pushing the body towards the right. But look at the line of action of upper P and smaller p. They are not in the same line, and hence we are now talking of a situation in which two equal and opposite parallel forces, where the line of action is not matching, they tend to tear a body apart. What will happen to body? Consider two plates are joined by a rivet, vertical rivet, which is shown here in the figure. When the force is sufficient enough to pull it apart, what will happen? At the section which I am showing here, at the contact surface, at this tangential area, the rivet will break down, and this is called shearing. If you look at this force, the resisting force which is coming on the rivet head is P here, and the resistance is generated on the top surfaces on the area, and these stress vectors are tangential to the area. So this is known as shear stress, and this action is known as shearing. So in general, what we say, when two equal and opposite parallel forces which are not in the same line acts on the part of body, then one part of the body tends to slide over or shear from the other, like upper plate is sliding to the left and lower plate is sliding to the right, and they are shearing from the other across any section, and the stress developed is termed as shear stress. The shear stress intensity is defined as tau equal to P by A. Tau is used to denote the shear stress. The shear stress is always tangential to the area over which it is acting, like it is shown here at the rivet cross-sectional area. It is tangential, not normal to the area. Now consider a shear stress which is acting on face AD and CB. These are equal and opposite forces which are stresses which are acting in not in the same line of action, but they are equal and opposite, separated by a distance x as shown here. Now what will happen? They will try to rotate this block of unit thickness in clockwise direction as I am showing here. But for equilibrium, then it is necessary that something resisting torque should also resisting movement should come in the anti-clockwise direction. So automatically there are generation of a vector tau dash which act on these two planes which are shown here on AB and CD plane, and they are trying to rotate the body in the opposite direction, that is anti-clockwise direction. So if you take the moment, if the distance AB is x and distance BC is y, the active couple which is due to the shear stress is the distance for the stress is tau, and how much is the area? The block is of unity thickness, and this AD distance is equal to y. So the area is y into 1 of this face AD is y into 1, and these two faces are separated by distance x. So the moment is stress multiplied by area, that is equal to force multiplied by the distance separating them, that is x. Same way we can look at the tau dash plane. So tau dash, what is the length of CD plane? CD plane length is x, and perpendicular area, perpendicular depth would be 1. So the area of this would be tau dash into x into 1. So this is the force, and how much is the distance between these two? So this plane, top plane and bottom plane, the distance between top plane and bottom plane is y. So multiply it by y. So if you look carefully, this comes out to be as tau into y into 1 into x equal to tau dash into x into 1 into y. Look carefully, x into 1 into y or y into 1 into x are same, and hence it on simplification it gives tau equal to tau dash. So it says whenever there is a shear stress existing on any plane, corresponding uh, on perpendicular plane, the complementary shear stress is automatically generated, the magnitude of which is equal to the original shear stress. So to sum up, the complementary shear stress on the transverse pair of faces is known as the complementary shear stress. The magnitude of balancing shear stress is equal to the applied shear stress, that is tau is equal to tau dash. Every shear stress is always accompanied by one equal complementary shear stress on the perpendicular planes. It is generated automatically, and owing to the characteristic of complementary shear stress on the equilibrium of members which are subjected to shear stress near a free boundary on which no external force is acting, the shear stress must follow a direction parallel to boundary. This is because any component of shear force perpendicular to the surface cannot exist without any complementary shear stress on the boundary. So that's an important point to carry. Now, one important property. The complementary shear stress may cause an early failure in anisotropic materials such as timber, which is weaker in shear along the grain than normal to the grain. So you see the red line. If you try to cut the timber perpendicular to the grain line, then it is difficult to cut. But if you try to cut it along the green vertical arrow, which is along the grains, then it is easy. This is because of the property and anisotropic properties of the timber. So it is there you can take advantage of the complementary shear stresses and anisotropy of the material. So the question for today is that find out the situation like which we have shown one in the example in the today's lecture, how the complementary shear stress can be of help in cutting anisotropic materials, and you have to comment with the examples which are different from what we have discussed in this lecture today. So the references for today's lecture that our textbook is by Dr. S.S. Ratan, The Strength of Material by Tata McGraw-Hill Education book, and the Timoshenko and R.K. Bansal are used as a reference book. So the main textbook is by S.S. Ratan, and most of this lecture is being taken from this book. It is a good book and we thoroughly recommend it to you. That brings towards the end of today's lecture on the stresses. This is your instructor, Dr. P.K. Asnan, signing off. Thank you for your kind attention and happy learning. Take care. Thank you very much.